Alex Manassa, and today we're going to learn about I2C. Now, what is I2C? The I2C bus is a way for data to get exchanged between integrated circuits. It's called I2C for inter-integrated circuit communication. It's got two wires, and I'm going to pull out my little cursor here so I can mark up. It has two wires, which is one of the important parts of it. Other protocols need multiple wires, and other protocols need more wires used for every piece that's, every chip that's on the bus, right? But what this does, what I2C does instead, is it has addresses for everyone who's on the bus. Imagine if you have a long street. You don't have a driveway for every single person. Instead, everyone has their own street address. That way I know where to send messages and what kind of messages I can send, right? So it is a master-slave protocol. And what that means is that the master provides the clock. That is really the main difference. The master also, in I2C, initiates all of the communication. So think of the clock like a conductor, right? The conductor says when to play the notes, kind of, or, ostensibly, right? The slaves will sort of do at the master's bidding. Of course, these days, because it's 2020, master-slave, those words are problematic, is what people say. I hate that phrase, problematic. You can also call this, I guess, chip select. There is no other name for it. Engineers do not update their vernacular to make it politically correct. If you're offended by this, then I would ask you, have you ever been a slave, or are you a slave now? And I think the answer would probably be no. If you are a slave, and I do know people who have been slaves, they usually have real problems like slavery. So don't be offended on their behalf. They got bigger problems. If slavery offends you, you should probably go free some slaves. You can find them here in America. Probably close the border. That's enough of my political rant here. It's called Master and Slave. Get over it. If you don't like it, you can find another channel, I guess. Hopefully you get some value out of this, though. You can have multiple slaves share the single bus. Each slave has an address, right? Further, each slave has multiple data registers inside of it. So if you have your master, right? You got your big M for master. He's going to talk to a bunch of slaves just on this bus. So here's a square, here's a square. They're all going to share the same wires. So here's the second wire. There we go. Okay. I'm going to put 3 of these guys on here. Boop, 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 and boop. All right. I'm going to call this guy 0, 1. This guy is going to be 1, 0, and this one's going to be 1, 1. How about that, right? So if I say, hey, slave number 0, 1, he's going to say, oh, yeah, what's up? Then he's going to reply, and then I'm going to say, show me your one of your data registers. Let's say it's data register 0, okay? So you got 0 and then 1 inside, right? 0 and then 1. So slave 1, 0, and 1, 1 both have a register number 0, register number 1 inside of it. So I can go and read those. I can write those if I'm the master. We're going to talk about how that data gets exchanged and how this whole operation goes. I'm going to show you some scope traces, and hopefully it'll be really cool. Now, the scope traces I gathered from this setup right here. All right, I've got a really, really fancy analog discovery 2. There's also a digital discovery. Analog discovery 2 is like $400. The digital discovery is like $200. There's also a open source version, I think, that's only $100. All of them will work the same for this. Okay, I got analog discovery because I wanted O-scope probes. But what you see here, pull up my cursor again, is that you have the 2 lines, S data and S clock, as I described before. The clock is the cadence of the messages, and the S data is the actual data itself. All right. I've got the micro right down here that's actually sending the data, and he is located right there. All right. Ignore this interrupt guy. He's an extra pin on there. It just lets me know that the accelerometer has data. Oh, by the way, this slave in particular is an accelerometer, which is going to help me with the Americhetti project. What it does is it measures the acceleration of objects, right? I'm going to put it on the tip of the machete. It's going to tell me how I'm swinging it. I'm going to integrate it twice. Once to get velocity, another time to get position. Once I know the position, I can blink the lights with that and make an American flag or something else. All right, here's the sensor itself. The sensor itself is actually really tiny. It's actually this little guy right here, that tiny black chip you see. That's the accelerometer. Okay, so that's my setup. Let me just there we go. Okay, just a little bit of mumble. Before we get in, and I'm just going to another little tease here. There we go. The way the protocol works, because you're sharing this bus, it's like only one person can use that street at a time. Like, imagine it's a really, really small street, okay? everyone has to share. Now, the master has the clock. So now everyone has to share the data line, right? The way that you kind of initiate this whole conversation is, first things first, the master is going to pull the data line low without changing the clock. So that's kind of like you're just going, you're making a signal. You're going, somebody goes, let's go with that analogy. The master sort of goes, get ready. All right. So he's going to pull the data line low. The way that all the bytes are read, and I don't have a graphic for the second one, address, write, read, because it's pretty complicated. They're going to be on the next slides. You're going to send a 7-bit address, which is the slave's name, right? The slave's address, okay? And you're going to have another bit at the end of it to make it a full 8 bits, to make it to tell it whether it's a read or a write. A write is going to be a 0, a read is going to be a 1, all right? The slave is going to acknowledge the master's messages, okay? And the way the slave does that is, since everyone is sharing the line, what the master does, he lets go of the line. The line springs back up, and the slave can continue to hold it down. If the slave keeps holding it down, the master knows the slave is listening, all right? A knack, which is a no acknowledge, is the exact opposite. That's when everyone lets the data line go, and it just naturally pops up, okay? We're going to see that. Oh, whoops. I always do that. Whoop. All right, here we go. This is an example of a master talking to a slave with a name hexadecimal F, which is 1111. You're going to look at, it wants to see it wants to write a value to a register that's at 1B, and it wants to write the data of 78 to that register, okay? So the way we're going to do this here is, you have your start bit, and here, I'm just going to circle my best. It's going to get a little cluttered. It's going to get a little cluttered. That's the start bit, okay? That's the S. The sequence up here is from the data sheet, and we are on this sequence number 1, right? So sequence number 1 is here, okay? So the S is the start, all right? This is in the data sheet. I'm just saying it out loud so you guys to know, but this is from the data sheet of, I think it's the KJ03 or something. It's a Kionics 3-axis accelerometer. All right, so next one is the slave address plus a W bit, okay? Now the slave address, device address here is F, okay? So you have the first 7 bits, which is right here at the rising edge of the clock. You have the data that exists at the time of the rising edge of the clock. That's the data that you want, right? So we're just going to grab the rising edge and pull it down. And you see the first 3 are all zeros, 0, 0, 0. Now, the next rising edge, it's a 1. Next rising edge. That one went a little skew. Sconce. A little win askance. Is that a word? Feels like a word. Put in the comments if askant is a word. Askance, askant. All right. So what we have here is 0, 0, 0, 1, 1, 1, 1. Okay. So that's our 7-bit address right there. And then we have our read-write bit. Now, a read-write bit here, as I said before, write is 0. Okay, so this is a write bit. And you can tell that my super fancy... let me erase that out of the way. My super fancy logic analyzer has identified that this is hexadecimal F with a write bit, because I told it that it's an I2C bus, okay? And you can see the S clock line, you see the S data line. Sorry if I didn't make that clear. All right, you see the acknowledge. Now remember, an acknowledge is when the slave holds the line down while the master clocks, okay? Next one is more data. So we're following this graph here. So we've got the acknowledge. Now the master needs to send the RA, which is the register address. That's this guy right here, CTRL1. Okay, and that's 1B. This is from the data sheet. Okay, so if I'm throwing numbers at you, it's because it's from the data sheet. You see, all right, 0, 0, 0, 1, 1, 0, 1, 1. If I were to plug that into Microsoft's calculator, go to programming mode and enter that into the binary, it would show me that that is hexadecimal 1B. And you see that in the logic analyzer right there. All right, slave's going to acknowledge one more time, as it says up here in the graph to do, or the table to do. Now I'm going to send the data that I want to write to sub-address 1B, or register address 1B, okay? So here is my data, 0, 1, 1, 1, 1, 0, 0, 0. And that is 7, 8, right? Because 7 is 0, 1, 1, 1, and then 8 is 1, 0, 0, 0. So 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. And there's a final acknowledge, which is right here. And there's supposed to be a stop bit. I don't know why I didn't send it. I might have forgot to put that in the software. but there's supposed to be a soft stop bit. And that might explain why some glitches were happening earlier. So there you go. That is a read operation. Or sorry, that's a write operation. A write operation is very straightforward. A read operation is a little different, because what you do in a read operation is you actually write the sub address of it. You go ahead and say, hey, slave 0f. Okay, I want to know about the write to the sub address. So I want to write to you, slave, at device address 0f. Okay, and I'm going to write the address of the register that I want to read, right? Then I'm going to restart everything, and then I'm going to say, okay, device address 0f with a read bit. Now and I'm going to give you 8 clocks so that you can then tell me the data that's at that register. Okay? So remember this is S clock and we've got S data. We are in sequence number 3 here. So I'm going to switch over to red. You see that we have S. We got our start bit. Okay? We got our SAD plus W. So we have our device address plus W, and that's reflected right here in the logic analyzer. It's already interpreted for us. Let me erase that bit because I'm being a little inaccurate there. I'm going to put all the protocol framing stuff underlined in red. All of the good data stuff that I really care about is going to be in blue. Okay. I'm just going to go ahead and underline all the red stuff now. See, I sent a stop bit on this one. You can see it here. I wonder if I just had that out of frame or something. Okay. All right. So you see here on the sequence 3 in the table up here, you see that we start. We're going to send the device address plus a write byte, which is exactly what we have here. There's the write byte. We're then going to send the address of the register that we want to talk to. Oops, wrong one. I'm going to send the address of the register that we want to talk to, which also happens to be 0f. That's just a coincidence. Then we're going to, the slave's going to do its acknowledgement. Master's going to initiate a restart, which is this SR. SR is for restart. What letters they use make no sense to me. It just is what it is. That's from the data sheet. Every single data sheet I've read tends to have the exact same convention, so I wonder if the people who made the protocol did it. Let's blame them. Then we're going to say, hey, device address 0f, I want to do a read. And here's the read bit. See how on the transition upward? Ugh, I butchered it. I killed it, Gilbert. At the transition upward, you have a 1 on the data line. That means you're sending a 1, and a 1 corresponds to a read. Okay? Next, we've got our data, and this is the data that we're reading out. So I'm going to circle this in green here. See that? This right here is the data. And you can see it is 0, 0, 1, 1, 0, 1, 0, 1. So 0, 0, 1, 1 is 3. This is 0, 1, 0, 1. That's 4 plus 1. That's a 5. So that's 3, 5. There you go. Bob's your uncle. And then you have a knack. So no acknowledge means that the slave, and it looks like here the master is actually the one who's letting the line just go up, right? So the master is just letting the line go up, and then the master initiates the stop bit. Okay, I didn't mention what a stop bit is before, but it looks like here it's when you hold the line low while toggling the clock high. All right, and that is how I2C works. Now, I know it's a lot of information. I went fast because I value your time, and I also know that you have a little pause and rewind function down below. So hint, 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 make good use of that. You're not going to sit here and watch a video and then have everything just make tons of sense, because that would be like an hour-long video. I'm not going to force you to go through an hour-long video. You can rewind, you can recheck, and look at this stuff in detail. If you want to follow along, what I suggest you do is take the graph, find an area where I haven't butchered the graphs here. All right, I'm even going to erase all this stuff here out of the way. So you can just grab your frame right now, grab it right now, and using the data lines shown here and here, right, between the brackets I'm making, go ahead and see if you can make that correspond to what's above. Now, I know this one right here is a little small. That one is the start. Okay, that's the start. That's your first gimme. The rest of it, go through and print it out, read it, take a screen cap. If you hold Windows key, Shift, and then S, you actually can take a cropped screenshot of your screen. It like freezes your screen in place so you can like drag and grab a rectangle. Do that, put it into Paint, try and make sense of it. You will be much better for it. This is how chips communicate to each other. If you don't understand this and you have a problem with chips communicating to each other, you're not going to know how to solve that problem, okay? So knowledge is power. Get powerful, get huge, get swole. I will see you guys next time. This has been the Alex Manassa. I appreciate you guys sitting through the video and learning. If you like the video, please hit the like button below. If you want to see more of these videos, hit the subscribe. And if you think this is going to be useful to somebody else out there who wants to learn about electronics, please share the video. It's senseless. These videos are free. I put them on here for free for you. It's all for you. Any Misery fans out there? No Stephen King fans? All right. I will see you guys later. Have a great day, and I will see you guys next time.